Hello beginners, this is BeginElect. This channel is for beginners who are interested in electrical installation and electronics. Today we are going to talk about rectification. We are going to be talking about rectification in details, all about rectification circuit, half wave rectifier, full wave rectification, and bridge rectification. How to calculate voltage root mean squared. So let's start from biasing. It's very important you know about a diode, because if you know about a diode, it's easy for you to understand how to test a transistor. When we are going to talk about transistor, you're going to understand better if you know about diode. This is a transformer used to convert AC voltage to DC voltage. So you can see this transformer has the secondary winding, and this is the primary winding. The secondary winding is 220 volts supply. This transformer is a 14 volts DC and 220 volts AC supply. There are different types of transformers. Some transformers has auxiliary winding depending on the use. Some transformers has center tap. This transformer symbol is like this. This is the symbol of this transformer. This is the secondary winding, and this is the primary wind. This is the primary winding, and this is the secondary winding. The primary winding is higher in number and higher in resistance. How you will know a primary coil is when you test the resistance is always bigger than the resistance of a secondary winding. So today let's start from biasing. These are general purpose diodes. This is IN5401 diode, general purpose diode. There are 4 in numbers. This is 100 volts 3 amps diode. So probably as a beginner in electronics, you have been hearing about rectification, and you have also been hearing about biasing, forward bias and reverse bias. This is a diode. This is a diode. As you can see, this part of the diode, there is a silver line on it. This part of diode, that silver line is on it, is the negative, the cathode, and this part that there is nothing on it is the this part of the diode is the negative, the cathode. As you can see, how you will identify the cathode is it has a silver line on it. The end that has silver line on it is the cathode. Then this end is the anode, positive. This is the anode. And for a diode, voltage drop is between 0.4 to 0.9. When you test this with a multimeter, the voltage drop you will see on the screen of the multimeter should be between 0.4 to 0.9. Let's check. This is my multimeter. As you can see, the multimeter screen. I switch it to diode mode. I'll switch my multimeter to the diode mode. I press the positive probe of the multimeter. I will place it on this side. See this side? I place the positive probe here. This is the negative probe. I press it on the side with the silver line. As you can see the reading. Negative probe. As you can see, the reading is 0.5. 0.567. So it's reading 0.5. That means it's a good diode. What I just did, placing the positive probe at the positive terminal and negative probe at the negative terminal, what I did is forward biasing. I have forward biased this diode and it showed me a voltage drop. So when I reverse bias the diode, I connect the negative probe on the positive side. And the positive probe on the negative side. This is called reverse biasing. As you can see, my multimeter is showing no reading. When you reverse bias a diode, it's like changing the polarity, connecting negative to positive and positive to negative. The diode do not conduct in reverse bias condition. When negative is connected to positive and positive is connected to negative, it will not conduct. It acts as an open circuit. So let me also demonstrate using a light bulb. This is a diode. As you can see, the positive, I've connected the positive thread here, the positive wire to the positive. As you can see, what I'm doing. Connected the positive side of the LED bulb to the positive side of the diode. As you can see, the diode is forward biased. As you can see, the light bulb is on. It's forward biased. That's why the LED is glowing. As you can see, the LED is glowing. When I reverse bias it, I turn it around. As you can see, I have turned the negative. As you can see, the negative is facing this way. This is reverse biasing of a diode. And in the reverse bias condition, it does not conduct electricity. Current will not flow. Current can never pass through this diode because in this condition, it is reverse biased. So let's talk about rectification. Is the conversion of AC current to DC current. So let's talk about the types of rectifications. Let's talk about half wave rectification. Half wave. Half wave rectification. This one makes use of one diode. The half wave rectification makes use of one diode. This is the transformer. This is the diode connected. This is the negative side. This is the positive side of the diode. Then we connect this to the positive, to the capacitor. This is the capacitor, negative with the positive. In half wave rectification, you notice that AC voltage is a sinusoidal voltage. It has a sine wave like this. So as you can see here, during the positive half cycle, this is positive, this is negative. During the positive half cycle, when the current flows from positive to negative, during the positive half cycle of the AC current, this is 220 volts AC, this is 14 volts DC. As you can see, during the positive half cycle, this diode is forward biased. It's forward biased, and current flows from the diode through this capacitor to the back to the transformer. It is forward biased. Therefore, you get a waveform like this. So during the positive half cycle, during the negative half cycle of this, during the positive half cycle of this diode, the negative half cycle, the diode is reverse biased. When the negative current will flow, the diode will be reverse biased. As you can see, current cannot flow, so you get only one sine wave. Through this, you get only one sine wave instead of two, because the positive voltage, which is the positive half cycle, which is from here to negative, during the negative half cycle, the polarity will change. This is a transformer. This is This is the AC, this is the DC. This is the diode, capacitor. The shaded part of the capacitor is the negative. So during the negative half cycle, this positive terminal will turn to negative. And this terminal will turn to positive. Because after one cycle, the terminals will change. So as you can see, a positive voltage cannot flow through this side. A positive voltage cannot flow. This voltage cannot flow again. You get only one cycle. Because when current tries to flow from this side to return to the coil, this side will be reverse biased, and it will block. The diode will not allow current to flow. It allows current to flow only during one cycle, when the current is moving from positive to negative. But when the current tries to move from this side to this side, you see that this diode becomes reverse biased, and you get only one cycle instead of getting two cycles out of it. You are supposed to get two cycles, but you will get only one cycle. This is why this half-wave rectification is not efficient, because when you get only one cycle of the voltage, there is a lot of power losses and it's not efficient. This is how half-wave rectification is done. Let's demonstrate it using a light bulb. This is our capacitor. This is the negative side of the capacitor connected. Connect the negative side of the capacitor. As you can see, the negative side of the capacitor is shaded. This is the positive side. We connect the positive side to the positive side of the As you can see, this is full wave, half wave rectification using only one diode. As you can see, the light bulb is on using only one diode. From the transformer to diode, from diode to capacitor. What the capacitor does is to purify this diode changes the AC to DC, and the capacitor will purify it, remove impurities, will make it smooth. When this diode converts AC to DC, capacitor will make it smooth, because the DC in the diode is a pulsating DC. Pulsating DC means DC that contains ripples. And if you're using only a diode without capacitor, or the capacitance is not enough, you see, when you try to power your monitor, you will see lines on the monitor. The monitor screen will not be smooth. You will see lines as if you are tuning a television station. The line, you will see lines on the monitor as if you are trying to tune a television station in your TV. Those signs you see is what is called pulsating. Pulsating DC is a DC that contains ripples. When you use a diode to convert AC to DC, the DC at that stage is always pulsating DC. But when you connect a capacitor of appropriate capacitance, that capacitor will remove the ripples. Okay. There is another rectification called the full wave rectification. So full wave rectification circuit is like this. It has a center tap. And two diodes are connected like this. With the negative side facing like this. The center tap transformer is this is a 14 volts transformer. This is 14 volts positive, 14 volts negative, and this is the zero. This is the ground. This is the ground. This is how the circuit is being connected. The negative side of the capacitor will come here, and the positives will be connected together like this. This is how it is connected to the capacitor. I do not have a center tap transformer to demonstrate this for you. So but let me explain how it works. Now during the positive half cycle of the AC current, this is AC, positive, negative. During the positive half cycle, as you can see, the diode is forward biased and it moves from the positive of capacitor to negative, return to ground through here. So you get one ripple. As you can see, during the negative half cycle, this terminal will become positive. This is the positive half cycle. Positive, negative, negative. During the positive half cycle, as you can see, the current flows from here to positive of the capacitor, enters the negative of the capacitor and return to the ground through here. So a full wave rectifier must be center tapped transformer. A full wave rectification is achieved with a center tap transformer. You cannot use a transformer that is not center tap to achieve a full wave rectification. I will demonstrate that for you later. So this is the second half. The center tap. This is the diode. This is the diode. This is the negative of the capacitor. The two are connected together, the two diodes. This is the positive of the diode connected together. So during the negative half cycle, this terminal will become positive and this terminal will become negative. As you can see, the diode will also conduct from here from the positive side. As you can see, the diode is forward biased, so it will conduct, enter the capacitor and goes to the ground and return again. This is the movement of the current. This is the movement of the current. Current will move through here, ground. So you achieve another ripple. In the positive half cycle, you got one ripple. During the negative half cycle, you got another ripple. As you can see, this voltage is positive voltage. It's always positive voltage. You can either get a positive voltage or a negative voltage depending on how you put your stand. If I change my diode like this, if I put the diode like this, this voltage is a positive voltage. So we have covered half wave rectification and full wave rectification. Another type of rectification is the bridge rectification. The diagram of the bridge rectifier is confusing the way you see it on textbooks, but I will draw it in a way you understand here. This is the transformer. This is the primary, plus, minus, plus, minus. This is the primary core that will be rectified. Here we use 4 or more than 4 diode, but the diode must be 4 in number for it to be bridge rectifier. We use 4 or more diodes. So these are you can see these diodes. One of these diodes is forward biased, one is reverse biased. This is how you connect it. Put one like this and one like this. As you can see, this is the negative part of this is the AC part of the current, and this is DC. This is DC. This is 220 volts. This is 14 volts. So I'm trying to rectify this current, this voltage. This 220 volts is converted to 14 volts with a lesser number of turns of coils. As you can see, this 220 volts contains a lot of coils, greater number of coils. So when this voltage is transferred to this voltage by induction, due to the fact that this coil is less, the voltage reduces and the current increases. So So this is a rectifier. Connect these two here. So these two are the negative. These two that are reverse biased are negative. This is the negative side. You connect them together. You connect these two together. This is the capacitor. Let's label this A1, A2, A3, A4. So during the positive half cycle, A1 is forward biased, A2 is reverse biased. So current flows from A1 down here, A3 is forward biased, A4 is reverse biased. Therefore current flows from the DC flows from A1 to A3. The current flow from A1, it enters the capacitor, the negative side of the capacitor. As you can see, it cannot flow through here, it flows through here due to the fact that this diode is forward biased. So you get one ripple instead of this ripple being like this, being sinusoidal. This is the positive half cycle. So let's draw the negative half cycle. Let's draw the negative half cycle. This is the negative half cycle. This is AC. This is DC. 220 volts, 14 volts. So this is the this is the The capacitor negative is to join together, join to the positive of a capacitor. Capacitor is used to purify the ripples. So during the negative half cycle, this terminal becomes positive and this terminal becomes negative, because AC current, after one cycle, the terminal polarity changes. So as this terminal becomes positive during the negative half cycle, you now see that this diode is forward biased, whereas this is reverse biased. A1, A2, A3, A4. As you can see, this diode is forward biased. It's from here, it enters the positive of the capacitor and moves to the negative of the capacitor. It cannot pass through here because here now becomes reverse biased, but this is forward biased. It passes through here. You get another ripple. So you get the full ripple. So the most efficient way of conducting AC to DC is either is the center tapped, because it's the center tapped full wave rectifier. Because here you use 4 diodes and all the 4 diodes are conducting, and you are getting the 2 ripples. This is AC signal, this is DC signal. This diode converts this signal into this signal. You get the 2 signals, but in half wave rectification you get only one, thereby losing the other signal, which means loss of power. So as you can see, in center tap full wave rectification, you are using only 2 diodes. Only 2 diodes are conducting, thereby you are saving power. But in bridge rectifier, you are using 4 diodes. The 4 diodes are conducting and you are losing power. So the most efficient way of converting AC to DC is through center tapped full wave rectification. So there is what is called ripple factor. Ripple factor so the ripple factor formula is ripple factor is equal to square root of voltage root mean square over DC voltage minus 1. V root mean square over DC voltage minus 1. So you have also the peak voltage. So ripple factor is used to calculate, to determine the smoothness of the ripples. Because when you convert AC to DC, ripple is like impurity. So a DC voltage that contains ripples is a pulsating DC. Pulsating DC means that the DC is not smooth. Sometimes when you plug your your power supply to your monitor, you see lines on the monitor as if you are tuning a channel, a TV channel. That is because it's either the capacitor is not enough or the capacitor is dead. Because what the diode does is to change AC to DC. It does not remove impurity. Then the capacitor will remove the impurity. So let's talk about this voltage root mean square. Okay, let's talk about peak voltage. The peak voltage is the maximum voltage that the transformer can convert from DC to AC, from AC to DC. For this transformer, you see it written on the body of the casing of the power supply. For this, it is 240 volts. 240 volts is the peak voltage. But the voltage root mean square is different from the peak voltage. So I will show you the simple way of calculating voltage root mean square and peak voltage. Peak voltage is the maximum voltage that a transformer can convert from this AC to DC. The voltage root mean square is the voltage, is the AC voltage that is the AC voltage when given the same resistance as a DC voltage, we produce the same heat as that DC voltage. Voltage root mean square is a voltage, is an AC voltage compared to a DC voltage that will produce the same heat as that DC voltage when given the same resistance. So for instance, if this is AC voltage, this is AC, this is 10 volts. This is let's say this is 20 ohms. This is AC, then you have DC. You have DC. Sorry, this is the light bulb. 10 volts, 20 ohm. 20 ohm. So let's see if we can calculate the power V equal to IR. 10 is equal to 20. 10 is equal to 20I. 20I is equal to 10I. 10 over 20. I get the current equal to equal to 0.5 amps. Then P is equal to IV equal to 0.5 times 10 equal to 5 watts. This is equal to 5 watts for DC, but for AC it's not the same. So let's talk about let's say AC voltage has AC voltage has a peak voltage of so this is AC voltage, the positive. This is the positive waveform because it's sinusoidal. It has positive and negative wave. Let's take the positive part. This is the half cycle, which is 180. This is 180 because half a circle is 180. This circle that AC voltage goes through is equal to a circle. This half and this half is equal to a circle, so it's 180. Then the peak voltage, let's say the peak voltage is 20. The peak voltage is 20 volts. If the peak voltage is 20 volts and you are asked to find the V root mean squared when the peak voltage is 20 volts. If you are asked to find the V root mean squared when the peak voltage is 20 volts, what you have to do is to divide. So as you can see, here is the peak. The center here is the peak voltage. And the formula for dividing the voltage is 180 over the number you want to divide it into. Let's say we want to divide this circle into this half circle, semicircle, into 180 into 10 parts. Then you say 180 divided by 10 parts. It will give you 18. to give you a thing. So let's divide it into 10 parts. These are 10 equal parts. So let's find AC voltage whose peak so peak voltage 20 volts, and this is 180. So V root mean square. So let's find the peak voltage of 20 volts, AC peak voltage of 20 volts. Let's find the V root mean square using only the positive half cycle. So what we do is we divide this into a number of equal parts we want. Let's say we want to divide this semicircle into 10 equal parts. Let's divide it into 10 equal parts. So let's divide it into 10 equal parts. This is 1, this is 2, so the peak voltage is 20 volts. We have 20 volts peak voltage. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I want to make it shorter. I want to make it 10 or less than. Let's redraw this. Let's redraw this. Okay, please don't mind my drawing. Assuming you have a peak voltage of 20 volts and you're asked to calculate the V√min squared. So you divide this semicircle into how many number of equal parts you want. This is time. Then it's, as you can see, you know that this is 180 degrees. Semicircle is 180 degrees. You divide it into the more number you divide it into, the more accuracy you will get. Assume, let's call this is 8, this is 8 volts, this is 11 volts, this is 16 volts, this is 18 volts, this is 20 volts, this one is 18 volts, 16 volts, 11 volts, 8 volts, and 0 volts. So as we have divided it into number of, to get here and here and here and here, all you do is 180 over 10 equal to 18. Here is 18. From here to here is 18 plus 18, 36. From here to here, keep adding 36 to all these until you get here. But for us to get the V√min squared, all we will do is 8 squared plus 11 squared plus 16 squared plus 8 plus 18 squared plus 20 squared plus 18 squared plus 16 squared plus 11 squared plus 8 squared all over 10. Then you find the square root. So this is how you get the voltage root mean squared. So 64 plus 11 squared one to 1 plus 16 squared two 5 6 plus 18 squared 324 plus 400 plus 324 plus 256 plus 121 plus 64 all over 10 you find the square root of all this. V root mean squared is equal to 64 plus 121 plus 256 plus 324 plus 400 plus 324 plus 256 plus 121 plus 64. Divide by 10, 93. V root mean square equal to 193 squared. That V root mean squared equal to 13.8, which is approximately 14 volts. That's how you get the V root mean squared. So if you want to calculate the ripple factor, is equal to V root mean squared over DC voltage minus 1. That's how you get the ripple factor. So another one is the efficiency. Efficiency is equal to input voltage over output voltage. That's how you calculate the efficiency of the rectifier. So our channel X or YouTube channel X, BeginElect, BeginElect, because it's a combination of electrical and electronics. This is where you get to understand electronics as a beginner in electronic engineering. Like, subscribe, comment.